condensed matter version of what I told you is called Harper model. It came from Parles in 33 looking at magnetic field on two-dimensional lattice. And he showed that you can reduce it to one-dimensional Schrodinger equations. And this is now connected to butterflies and to Anderson localization. My example was simplest. I was only looking at periodic solutions and not almost periodic solutions. So yes, when we do the Navier-Stokes, there is no time reversal. Forward is different from future. And it turns out Hill determinants don't care about Lagrangian or Hamiltonian nature. They were just discovered in that context.
I'm wondering, why you insist on studying infinite systems or periodic systems? Physically, what happens if you...
you obviously don't believe in quantum field theory at all because, we quantize quantum fields always in a box. Every course will do it first in a box.
Oh, no.
Then we'll take the walls off to infinity.
Oh, no.
It's the same situation.
There are boundary field theories, which are important. You have special transitions.
Sure. If you have physical, so for example, what happens in pipe flow, there is a long direction, and the assumption is that you have exponential decay of correlation along the pipe. So, the turbulence here affects turbulence up and downstream in exponentially decaying way. And that's the assumption of, hyperbolicity this model has. So it's supposed to describe kind of uniform turbulence every place. Now, if you look in radial direction, I have boundary condition. And actually the cell, there's no translation, there's rotational invariance, which we always use because we get, M numbers in rotational direction. But I think you always, as a field theorist, want to first describe the infinite thing. And then physics might force you to look at von Neumann, Dirichlet for particular physical setting. But here the assumption is, everything is messy on a small scale and it's connected to its neighbors, but it's not connected 50 neighbors or 1,000 neighbors away. And that's the assumption we always do in field theory.
In a sense,
I think for the, the undergraduate course,
massive field theories, right? In that sense, you're studying massive field theories, not critical.
Of course, yeah. No, that's what it is. That's what's amazing. Cat map, which we always have, these poor cats are being sliced and mixed up and all that stuff. Cat map is actually a massive field theory. That's pretty amazing. I learned that from Vivaldi and Percival, from paper from the 80s.
Have you thought, Predrag, about continuous space and time? Because then you'll have neutral directions.
Yeah, so the way we do this, this has to do with my great, general program. I would like to do turbulence in Navier-Stokes before I do it in Young-Mills or gravity, just because the wisdom is so much greater in this field. And we always do the one-dimensional turbulence, which is typically either Burgers or Kuramoto-Shivashinsky. We do Kuramoto-Shivashinsky. So yes, we do it in totally different talk for Kuramoto-Shivashinsky. So we do it in continuum. And it's much more difficult and much more iffy. So, you won't trust our symbolic dynamics in Kuramoto-Shivashinsky. But, purpose of this talk is to tell you, when I say chaotic field theory, what do I mean? I claim this is what you mean. Now, there is one thing that's different, that field theorists who do it professionally don't do, which is, I'm forced to have fields on a torus. So it looks like Helmholtz or Navier-Stokes, but it doesn't have arbitrarily large fields on it. So that's different than what, chaotic field theorists do for their living these days. Everything is computable. Most of it can be done by hand.
Anatoly?
Yes, I have a question. What can you say? What can you say about the completely integrable system like Schrodinger model, nonlinear Schrodinger model, discretized? It is
I live in a world of what Aubry would call, and maybe Robert as well, Robert McKay, I live in a world of anti-integrability. So I'm looking at the cleanest possible anti-integrable system, meaning hyperbolic in a good, nice, strongly mixing way. So
yes.
I don't have a good answer to your question other than saying for S minus 1, I only get oscillatory solutions. So I only get, if you wish, KMs, but in high dimension. I only get, you know, toroidal solutions, which I guess are integrable in this particular model.
Yes, all your model were linear, yet this model is non-linear.
Yeah, absolutely. Non-linear. You know, I'm saying, look, the easiest way to explain cases by linear things where non-linearity comes from chopping it. That's what this integer m do. You know, so non-linearity comes either from chopping or bending. So, you know, Lorentz system chops and in ordinary differential equation, and Rossler system bends. And, you know, these are ways you get chaos. If you stretch and bend, because you have to fit the unstable manifold in a box. It's like putting a virus in a thing, you know. No matter how much you stretch, it has to sit in there. So you either cut it up. Now, easiest thing is cutting it up. That's Bernoulli. You know, it's either heads or tails. Or physically, we often have to do stretching. But anyway, this is much harder because it's very hard to avoid non-hyperbolicity in stretch and bend situations. That's a terribly hard problem.
Yes.
So I'm teaching you the simplest possible thing so you can answer anybody that, you know, ask a question. The linear thing explains chaos deterministic and also for field theory.